NanoStarChallenge consists in the pre-design of a small satellite space mission to the Moon in order to determine the feasibility of reaching the Moon with CubeSat technology. Our project name, CosmiQ. During the last 50 years, the fact that finding water ice in southern craters at the Moon's poles has become more and more interesting. For this reason, our team has developed a pre-design of a lunar mission with a 12U CubeSat in order to reach the Moon in a flyby. Thereby, the spacecraft will be allowed to obtain pictures around the Moon's surface and send them to Earth. Our team is formed by 6 aerospace engineering students, each of them in charge of several subsystems. Angel is our system engineer, and his main task is to manage the concurrent design process and the team organization. Moreover, he is responsible of power subsystem. Borja is in charge of mission analysis and orbit propulsion. Sergio in charge of communication and data handling. Pablo in charge of altitude determination and control system. Luis in charge of configuration. And at last but not least, Raúl in charge of thermal control.
The main science payload in the satellite is a 1-unit camera located in top area of the CubeSat, which will photograph lunar surface in search of water. The camera never points directly toward the sun when operating. This is during the lunar flyby. But our satellite not only carries the camera and the science payload. Additional payloads have been included in order to acquire more information about the lunar environment related to radiation and moon composition. One of these additional payloads is the commercially available X123 spectrometer. This is an advanced X-ray spectrometer whose ability to operate in space has been demonstrated in previous missions, so the risk factor is well known and not a big deal. Its objective in the mission will be to measure the abundance of certain minerals on the Moon's surface. On the other hand, we have included a radiation dosimeter, which will provide in-depth observation and the possibility to improve existing data on lunar radiation spectra. This instrument is especially important, since it will measure the radiation hazard level, preventing the satellite to operate in critical conditions and turning subsystems into hibernation mode. In addition, we will take advantage of the passage of the satellite through the Van Allen belt, where charged particle radiation is very present.
As our objective is to take data about ice water in the Moon, and it is known that it concentrates in the poles, particularly in the South Pole, the orbit used to accomplish the mission needs to have very well defined features. In the first place, the Ariane 5 launcher injects CosmiQ in a geostationary transfer orbit with a perigee altitude of 250 kilometers. The rest of the orbital parameters have been selected in order to direct the semi-major axis to the position in which the Moon is going to be when CosmiQ arrives. It is highly important having an orbit which contains the rotation axis of the Moon at arrival time to decrease the impulse component dedicated to change the initial orbit plane, and giving that impulse tangentially in the surroundings of the perigee to be the most propellant efficient possible. To minimize the global risk of the mission, the aim is reaching the Moon in the required way with only one impulse, avoiding making several propulsion systems start and stops. As said before, the maneuver starts in the perigee and finishes after 4,161 seconds of burn, spending 4.9 kilograms of propellant. At this point, CosmiQ is injected in a trajectory which will allow the satellite to fly by over the south pole of the Moon, collecting the required data and sending it to Earth. It is remarkable that the launch date was chosen to avoid eclipses for power efficiency reasons. Besides, for not contributing to space debris near Earth, the orbit has been designed to ensure an escape trajectory after the flyby. The propulsion system, which will take CosmiQ to the Moon, is formed by two 1-unit MPS 130 engines. This innovative engine is produced by additive manufacturing techniques and uses AF M315E as propellant. a recently used green alternative to hydrogen that provides us a better performance and more compactness. This power plant gives our satellite 3 newtons of thrust with a specific impulse of 260 seconds and will allow the mission to capture the details of the south pole of the Moon.
The attitude determination and control subsystem ensures that the pointing accuracy remains under the required level, and it prevents sunlight from hitting the payload. To guarantee the requirement's accomplishment, the XACT product from Blue Canyon Technologies is available. This component includes a star tracker, a sun sensor, an inertial measurement unit, and reaction wheels. For future iterations, there will be a backup system for reaction wheels desaturation. Along with that, 3 more sun sensors placed over different faces of CosmiQ controls the sun direction all the time.
The command and data handling selected for CosmiQ is the ComSpace A3200 nanomine computer. The A3200 nanomine platform is a high-performance, low-power radiation-hardened processing solution that meets the challenges of the space environment.
The main purpose of the power subsystem is to provide enough electrical power to all the different payloads and subsystems. The three main elements in the subsystem are the solar panels, the battery, and the power control unit. CosmiQ used the triple junction technology in its solar arrays to provide enough power to the system flight mode of the CubeSat. Only by covering one face with solar panels, enough power is provided to the vehicle, but more than are added due to safety and pointing issues. The vehicle has two nanopower BPX batteries to supply the extra power needed for the different modes such as propulsion, data gathering, or communication mode. Finally, the function of the power control unit is to provide the required input voltage to the different equipments of the system.
The communication subsystem is based on an X-band transponder supporting packetized command and telemetry, and one circularly polarized path antenna. This configuration provides a downlink rate of 256 kilobytes per second, with a bit error probability of 1 out 10 million when transmitting close to the Moon. The selected transponder is Iris. This CubeSat transponder is a low volume, mass, lower power, and cost telecommunication subsystem for deep space. Its main features include 0.5 CubeSat unit volume, 1.2 kilograms mass, and 35 watts DC power consumption when fully transponding at 3.8 watt radio frequency output. In addition, includes interoperability with ESA's Deep Space Network at X-band frequencies for command, telemetry, and navigation. Iris is designed with an environmentally robust architecture, including radiation-tolerant parts needed for deep space missions. The selected antenna is the Endurosat's X-band path antenna array. This small antenna provides 12 decibels gain and due to its small size, allows an easy installation in any outside space on the satellite. The ground segment is based on a 335 meters diameter deep space antenna with transmission and reception in X-band. This tracking station enables communication with spacecraft voyaging hundreds of millions of kilometers in space. The first antenna is located in the city of New Norcia, in Australia, the second one in the city of Cebreros, in Spain, and the last one in the city of Malargüe, Argentina.
So this was our project, CosmiQ project. Thank you so much for your attention. We have invested a lot of time and effort, and we have put our dreams and illusions to reach our final goal. The moon.